Hello friends, alpha and beta refers to the configuration at anomeric carbon, means carbon 1 for aldoses. For this sugar drawn the standard way, the alpha anomers has the C1OH position down and beta anomers has the COH pointing up. So you can see the structure of alpha D glycopyranoxide. Here OH position down and beta D glycopyranose OH position up. Now, a more full explanation examine the substituents on the two carbon flanking the ring oxygen, carbon 1 and carbon 5. Carbon 1 and carbon 5. In the case of glucose, if the anomeric C1OH and C5CH2OH as are on opposite faces, the enomer is alpha. If are on the same faces of the ring, anomeric carbon is beta. So you can see the opposite faces, that is the alpha, and same faces, that is the beta. Same faces, that is the beta. So you can see the alderic acid. Alderic acid, a carboxylic acid derived from the oxidation of an aldose where both ends are carboxylic acid. You can see the CHO and CH2OH. Both are oxidized to carboxylic acid. That is the alderic acid. Now, aldose, you can see the D-ribose and D-galactose. A monosaccharide with an alpha, an aldehyde or masked aldehyde functional groups. So, you can see, and this hemiacetal is a masked aldehyde since it is in equilibrium with the open chain aldehyde. This hemiacetal. Another examples you can see here the alditol. What is the alditol? An acyclic alcohol derived from the reduction of the aldose. So diglyceraldehyde and aldose, it undergo reductions and give glycerol and alditol, a cyclic alcohol derived from the reductions of an aldose. So D-glucose and aldose which undergo reduction, it gives the D-sorbitol and alditol. So enomers two sugars that differ in configuration only at the anomeric carbon, that is, the carbon bearing a hemiacetal. Now, in glucose, the anomers differ only in configuration at carbon 1. So, alpha D glucopyranose and beta D glucopyranose. So, alpha D fructose you can see and beta D fructose because it is in the same phase and it is in opposite phase. Now you can see anomeric carbon, the hemiacetal carbon of cyclic sugar, a chiral center which results from ring closure upon aldehyde or ketone in an acyclic sugar. So this is the anomeric carbon, hemiacetal form. Here you can see the anomeric carbon also in acetal form. So L and D refer to the absolute configuration of a sugar. A sugar is assigned L or D depending on whether the highest number stereocenter matches the configuration of L or D glyceraldehyde. If the bottommost chiral center in the Fischer projection has the hydroxyl group on the right, it is assigned the descriptor D. If it is on the left, it is assigned L. The enantiomers of a D sugar is always an L sugar and vice versa. The term D and L do not refer to the direction of optical rotation. So L glyceraldehyde, D glyceraldehyde, D glucose and L glucose and D ribose. Now you can see the disaccharide, a carbohydrate incorporating two simple sugar joined by a glycosidic linkage. Example, lactose is a disaccharide of galactose and glucose. So galactose unit and glucose unit. This glucose unit and this galactose unit combine through the glycosidic bond. Now you can see the acetal and hemiacetal. This is lactose, lactose, and sugar and maltose are other example of disaccharide. Now you can see two diastereomers which differ in their configuration only at single chiral center. You can see this OH, C2 epimers and C4 epimers. So D-glucose, D-mannose and D-tallose. So D-glucose and D-mannose are epimers at carbon 2. D-mannose and D-tallose are epimers at carbon 4. So D-glucose and D-tallose are not epimer since their configuration differ at two centers. Now you can see the furanose, a 5-member cyclic hemiacetal. 5-member cyclic acetal. So beta D fructose. Now beta D glucofuranose. So glycoside, what is the meaning of glycoside? An acetal or ketal arising from the condensations of the hemiacetal or hemiketal hydroxy group of a sugar with the hydroxy group of a second compound. The resulting product is not a reducing sugar since it is not in equilibrium with an open chain form. So ethyl glycoside or of D-glucopyranose are examples. You can see the hemiacetal. If it is treated with, then it gives the acetal glycosidic bond. So glycosidic bond, the CO bond linking the anomeric carbon of a sugar to the second component of the glycosides. Glycosidic bond here and glycosidic bond here. Now, if you check this Haworth projection used for a cyclic sugar, pyranoses and furanoses, clearly indicates stereochemistry arrangement of group or ring up and down, not meant to accurately convey the ring conformations. You can see the alpha D glucopyranose and beta D ribose. So if you check this hexose, a monosaccharide with 6 carbon, D-allose, D-glucose, D-lactose and D-fructose, a ketohexoses, and these are the aldohexoses. So you can check the mutual rotation in each case. The gradual change in measured optical rotations of a solution of pure anomers due to their interconversion through ring chain tautomerism. So alpha D glucopyranose, a specific rotation alpha D 20 is plus 112 degree, and beta glucopyranosa specific rotation 18.7 degree. Now if you put in the water, all interconverted into 52.5 degree, and that is the phenomenon, and this phenomenon is known as mutarotation. So if you check the ribose, xylose and arabinose,